Sauce here. This is a video lesson on differential equations. I'm going to introduce differential equations. And though they sound complicated, and differential equations can be sophisticated and complicated, the simplest understanding is a differential equation is one that contains a derivative. And a very simple one, dy over dx is equal to 6 times the cosine of x, is an example of a differential equation. It's an equation and it has a derivative in it. The derivative is solved for. We can think of, or we could be asked, what is the equation y that 6 times cosine of x is the derivative of? In simplistic terms, we could simply find the antiderivative of 6 times cosine x to get that equation. And that's true, but we're going to approach this with a complete process. This symbol for the derivative is very useful because it can be treated as a fraction and we can use the rules of algebra. On this fraction, if I multiplied by dx, then I would cancel out the division by dx. I'm going to multiply both sides by dx, and when I do, I get dy by itself is equal to cosine of x times dx. And now I'm going to do something to both sides that we may not have seen before, or you may not have realized that it could be done, and that is use an integral as an operation. I'm going to integrate both sides. What I do to one side, I do to the other, and the operation I'm choosing to do is to integrate. On this side of the equation, it's the integral of 6 times the cosine of x with respect to x. The 6 can be taken out and multiplied later. It's a constant. So I'm thinking, what is the antiderivative of cosine? It's sine of x. And the 6 then multiplies. I also need a plus c. On the left side of the equation, I have the integral of something. It's not shown. But of course, if you don't see something, it's implied that it's 1. This dy, we can think of it as a 1 dy, and the 1 is the integrand. So what I'm integrating is 1, and if it's with respects to x, the antiderivative of 1, well, in this case, if it's respects to y, then the 1 that I'm integrating becomes 1y. And it has its own constant of integration because this was an indefinite integral as well as the right side. They're not both the same constant of integration, so if we produce two of them, one on the left and one on the right, we might distinguish between those two as c sub 1 and c sub 2. But if there are two numerical unknowns, then we can combine them into a single numerical unknown. The sum of two things that are unknown can be made into one thing that is unknown. So these constants of integration that got created, I'm going to combine and represent on the right. And that way I get y by itself, and I can put the constant of integration as just the c that we're used to seeing. Here I have an equation for y. It was found by a process of solving this differential equation. If I think of finding the derivative of y, then it would turn back into what I started with. The constant of integration would go away because in taking a derivative, a constant becomes 0. Let's see another example of this. A little more sophisticated. I'm going to start with a differential equation because it's an equation that has the derivative on one side. This is dB over dt. and it's equal to 0.15 times b. In this differential equation, we can see something that's common for differential equations. We have the variable b and the derivative of that variable in the same equation. I'm asked to find b. I'm going to do what I did last time and separate this derivative notation, separate the dB and the dt by multiplying both sides by dt. Now, before I took the step to integrate, in the problem before, this would be where I integrated. But if I integrate now, I'll get an integral with respects to capital B. But if I introduce the integral now, I've got a confusion between the integrand having a variable b and integrating with respects to t. We don't want to mix the variables, so I'm going to need to get the b factor off of the right side by dividing both sides by b. When I do, I'm going to represent the division by b as a multiplication by 1 over b on the left side. And what's left on the right is a 0.15 dt. Now I'm ready to integrate. The integral of 1 over b with respects to b is the natural log of b, an integral property worth memorizing. It has its own constant of integration, but we're going to take the two constants of integration that are going to be created by these two indefinite integrals, and we're going to express them as one unknown constant of integration. The integral of 0.15 with respects to t is 0.15 t, and the constant of integration that combines both. Now, we're asked to find b, so I need to take the step of undoing the natural log, and the inverse of log base e, which is the natural log, is power base e. So if I power base e both sides, it'll cancel out with this natural log, leaving b by itself. And of course, there's an implication that b must be positive if it was the argument of natural log. On the other side, I have e to the 0.5t plus c. I'm going to use a power property that the power of a sum, or an exponent as the sum, can be represented as the product of two powers of the same base, where we take the parts of the sum and separate them so that they are represented with their own base. The reason why I did that is because I'm still working with this understanding that I can combine unknown constants into one unknown constant as long as the constant of integration is not involved with the variable. This e to the c is a number, and because c is unknown, then the number e to the c is also equally unknown. In other words, in this case, because this piece of the equation e to the c has no variable associated with it, then e to the c is what we call materially equivalent to the unknown c and can be represented just as c. So we have the final equation b times the constant of integration, or is equal to the constant of integration times e to the 0.15t. This is the best form because the constant of integration is expressed as a factor instead of a piece of the exponent of another factor. One more example. differential equation, we're starting with the derivative of y with respect to x is equal to e to the negative y. I'm going to separate out the derivative notation so that dy is equal to e to the negative y times dx. And like the second example, I'm not ready to integrate because I'm combining an expression. I have two variables. But I can move the e to the negative y over to the left side by dividing by e to the negative y. I'm going to represent that as 1 over e to the negative y. I could integrate now, but then my integrand would be something a little odd, 1 over e to the negative y. So I'm going to use power properties. I can change the sign of an exponent by taking the reciprocal of the base. In other words, the e to the negative y that's in the denominator is now going to be in the numerator. I'm not going to show the division by 1, and I get to change the sign of the exponent. Now when I integrate, the right side, the integral of 1 with respect to x is x. And e to the y is significant because a power whose base is e is its own derivative and its own antiderivative. So the integral of e to the y is e to the y. Both these integrations produce a constant of integration that I'm going to wrap up and express as 1, constant of integration on the right. And then if we're going to get y by itself, I need to take the natural log of both sides, which will cancel out the power base e, leaving y. And on the other side of the equation, take the natural log of the absolute value of x plus c.